Welcome back to our series on probability theory. I'm Mark Ledbetter. This is an in-class exercise number 3. So this is not a test, but it's similar to a test in that it's open notes, no open book, no electronic devices, but open notes in class, usually 30 to 40 minutes. In this exercise, it's chapter 2 problems, and the students were instructed to select 3 of the 6 problems, any 3, and complete them for a grade. Now, problems 1 through 4 use the information, and this is these numbers are made up, so please don't go out and start quoting statistics based on the situation here. I did take this from a real example, but I've changed the percentages. So I found a problem that talked about a certain species of fruit fly that have red eyes and white eyes. And we're going to say that it is known, so you assume that this is true, that 80% have red eyes. The remainder have white eyes. So I had to devise this system of doing different types of samples to emulate the different distributions that we studied, the discrete distributions. So we have this researcher that's in charge of randomly selecting fruit flies from the entire population. So again, this is not very practical, but this is the situation to make it fit these different distributions, at least approximately. So this researcher has several assistants, and they are randomly assigned to different locations and at different times throughout the day, throughout the population of this fruit fly, and where these fruit flies live or exist. And the assistants are using Bluetooth technology to stay in touch with each other and with the researcher so that we have information in real time. Of course, this is very unlikely in actuality, but it could occur. So problem number 1 says the researchers allows the assistants to collect specimens until the first fruit fly with white eyes, not red eyes, but white eyes, is observed. And we say to let X equal the number of specimens, these are fruit flies, that have to be collected or observed until we get the first fruit fly with white eyes. Okay? So P is the probability that a fruit fly has white eyes, and that's going to be 0.2. Provide the PMF of X along with its support. So we have that X is the number of specimens that's required to observe the first fruit fly. X is going to be a geometric distribution with P equal to 0.20. And so this is f of X is equal to P Q to the X minus 1, which is equal to 0.2 times 0.8 to the X minus 1, where X can equal 1, 2, 3, etc. So this is the support of X. Remember that the support or space of X is where the PMF has a positive value. All right? A positive value. So this is the answer to part A. B. Calculate the mean number of fruit flies one would expect to collect in order to observe the first white-eyed specimen. So we're asking for the mean, and for the geometric distribution, the mean, mu, is 1 divided by p, which is 1 divided by 0.2, and 0.2 is 1/5, so this is 1 over 1/5, so this is equal to 5. We would expect if we repeated the experiment over and over a large number of times, that we would have to collect 5 fruit flies in order to get the first one that had white eyes. Okay. And 20% of 5 is 1. Now, C. What's the probability that the researcher must collect more than 8 fruit flies in order to observe the first specimen with white eyes? Well, this is simply the probability that X is greater than 8. And for the geometric distribution, we learned that this is equal to Q to the 8th. Whatever this value is goes in the exponent, and so this is going to be 0.8 to the 8, and this turns out to be 0.167777216. And so everything, the instructions for this, which I have not included, tell us to round to the 4th decimal place. So I go out 5 decimal places, it's a 7, so I'm going to round to 0.1678. And that is the answer for part C. Part D, we want to find the probability that X is equal to 3. In other words, that the first fruit fly with white eyes is found on the 3rd specimen. So this is equal to 0.2 times 0.8 to the x minus 1. X is 3 minus 1 is going to be 2. So 0.2 times 0.64 is equal to 0.1280 to 4 decimal places, but is exactly 0.128. So that was problem number 1. If the student selected problem number 1. Now problem number 2 uses the same information, and now the researcher instructs the assistants to collect a total of 25 fruit flies and then stop. So X is the number of fruit flies with white eyes. I did not try to switch things up because I know on timed exercises it's stressful enough, and we don't need any little tricks like switching between white and red to completely throw off a student in their from what they're trying to do. So I'm really trying to focus on, do you know the material? In this case, what we have is we're going to collect a total of n equals 25 fruit flies. Again, there are 2 categories. They are white eyes or red eyes. So again, these are Bernoulli trials. So we have a fixed number of n. We have 2 categories. Because we're only selecting 25 fruit flies out of a very large population, we can assume that even though we're doing this without replacement, that these fruit flies are independent of each other by the 5% rule. So 25 is obviously less than 5% of the total population, which would only be 125. Or no, I'm sorry, divided by multiplied by 20, right? So 500. So we obviously have more than 500 fruit flies in the population. Now, so we have 2 categories. N is known and fixed. The trials are Bernoulli trials, so they're independent, and we have a constant probability of P equals 0.2 of getting a fruit fly with white eyes. So this means that X is distributed as a binomial with n equals 25 and P equals 0.2. And so this PMF is n choose X, P to the X, Q to the n minus X. And n is 25, so X, P is 0.2 to the X, Q is 0.8 to the 25 minus X, where X goes from 0, 1, 2, etc., up to n, which is 25. So this is the support of X, this is the PMF of X. So that's the answer to A. B, find the probability that at least one fruit fly specimen has white eyes. So this is the probability that X is greater than or equal to 1, which we don't want to do 25 binomial probabilities here. calculation. So we're going to use the complement rule to say that this is the same thing as 1 minus the probability of the complement of this, which will be x less than 1, not less than or equal to, because remember, a complement cannot include any elements of its that are the same as its complement, right? So it's a little difficult to say. So if if event A is x is greater than or equal to 1, then A complement would have to be that x is less than 1. Well, for the binomial, this is 1 minus the probability that x is equal to 0. Only one value can be less than 1, and that is 0. So I'm going to use 1 minus and then plug in the PMF, because sometimes it's easy to forget to plug the answer for probability x equals 0 back into the equation. And so then I find that students give me the complement, the probability of the complement event, not the event that's been asked for. And that's a very different probability. So this is going to be 1 minus 25, choose 0, 0.2 to the 0, 0.8 to the 25 minus 0. And so we have, if you remember, 25 choose 0 is going to be 25 factorial over 0 factorial over 25 minus 0 factorial. And this is just 25 factorial over 25 factorial. Remember that 0 factorial is equal to 1. Okay? It's defined as 1, not 0, or we would not have a probability. You divide by 0, everything's positive, you get infinity. So that can't be a probability. And we were subtracting, so that would be negative infinity. So definitely not. So 25, choose 0 is 1. A discrete value raised, not infinity, raised to the 0th power is 1. And so we're left with 1 minus 0.8 to the 25th power. And we find that this is going to be 0.99622. And it keeps repeating. And so to 4 decimal places, 0.9962. So the probability that we have at least one fruit fly with white eyes out of 25 is 0.9962. So very high probability. Now, we want to calculate sigma. Since this is a binomial, sigma is equal to the square root of sigma squared, which is the square root of n times p times q, which is 25 times 0.2 times 0.8. So this is going to be the square root of 4, which is very nice, so that we get a very nice answer of 2. The standard deviation is 2 fruit flies. All right, so that's the second problem if the student selected that problem. Now we're going to the third problem. And we're saying that the population of this species is known to be 80 million. Now, the key here is that all the units are in millions. And so we can just use the millions. So if the population is 80 million, that is capital N, is 80. 16 million have white eyes. We want to provide, and we're saying that X is the number of specimens with white eyes in our sample. And so N1, our category of interest, has 16 million fruit flies in it with white eyes, because this is white eyes and white eyes. So then N2 is simply N minus N1, which is going to be 64 million. Our sample, we sample 15 million, so N, little n, is 16. All right. And what we have is a hypergeometric distribution. So X is a hypergeometric distribution with n equals 80 N1 equals 16 and N equals, I wrote this wrong, it's 15 million. Little n, the sample size is 15 million. All right. Okay. So that means the PMF of x, f of x, is equal to, if you remember, it's N1 choose x times N2 choose n minus x, that's little n minus x, divided by capital N choose little n. And so this is 16 choose x and 64 choose 15 minus x divided by 80 choose 15. Now, if you recall, x is less than or equal to little n. It's also less than or equal to n1. And of course, n1 is less than or equal to n. So we have all these restrictions. Practically speaking, x is the number of specimen with white eyes. In this case, this is 15 million and n1 is 16 million. We choose the smaller one because we're only choosing 15 million fruit flies. We can't have more than that. All right? So x is equal to 0, 1, up to 15 million. So that is our PMF and support of x. B, what is the probability that 5 million of the sample fruit flies have white eyes? The probability that x is equal to 5. And so we have 16 choose 5, 64 choose 15 minus 5, divided by 80 choose 15. And using the calculator, it's much easier just to use a scientific calculator and to enter each of these combinations in there than it is to try to do manual calculations and canceling out. This would be a very tedious exercise. It can be done, but it's very, very messy. So this turns out to be 0.0997058, etc. To, I'm going to have to switch to another document and come back. There. Oh, and it took me back up there for some reason. So this is approximately 0.0997. So that's the probability, a little less, right at 10% chance that 5 million would have white eyes. So everything is white. So again, I did not change between white and red. Now the fourth problem, the last one to deal with the fruit flies, says the researcher allows the assistants to collect specimens until the 8th fruit fly with white eyes is observed. Let x equal the number of specimens required to observe the 8th fruit fly with white eyes. So x is a negative binomial because, again, we have Bernoulli trials. They're either white eyes or they're red eyes. We're sampling without replacement, but we're sampling much less than 5%. That is something I should mention for number 3, is that we're sampling 15 million. 15 out of 80 is greater than 5%. In fact, 15 divided by 80 is 18.75%, so much higher. So that's 18.75%, which is much greater than 5%. So by the 5% rule, we cannot assume that the 15 million sampled are independent, because we're doing this without replacement. So this is definitely not a binomial or any other distribution. All right, has to be the hypergeometric distribution. All right. So now back to number 4. Eighth fruit fly, R is equal to 8 and P is equal to 0.2. Negative binomial. Again, we have we're definitely going to take less than 5% of the population to get the eighth fruit fly with white eyes. And so we have the Bernoulli trial, independent, constant probability, and we have so the two categories, of course. And we do not have a set n. We repeat this until we get the eighth success, so to speak. So the PMF is f of x is equal to x minus 1, choose r minus 1, p to the r, q to the x minus r, and we plug in for everything except x, and we get x minus 1. R is 8, so 7 minus 1. I'm going to write this out in detail. 0.2 to the 8, not 7. 0.8 to the x minus 8. Okay, equals x minus 1 choose, this is 8 minus 1, so it's going to be 7. I was getting ahead of myself. 0.2 to the 8th, 0.8 to the x minus 8 in the exponent. And x has to be 8, 9, 10, or higher. X cannot be smaller than 8. We cannot choose less than 8 fruit flies to get 8 of them with white eyes, can we? So this is our PMF with the support. So B says, calculate the mean number of fruit flies one would expect to collect in order to observe the 8th white-eyed specimen. So the mean of the negative binomial distribution is R divided by P, and I always ask you to write out the formula and then plug in the values. And so R is going to be 8, P is 0.2, and this turns out to be 40. So quite a high number. We expect to have to collect 40 specimens to get 8 of them with white eyes, because our probability is only 0.2. Now C is, what's the probability that the researcher must collect 15 fruit flies? It doesn't say more than, less than, at least, at most. So this is exactly x equals 15, which is 15 minus 1, choose 7, 0.2 to the 8, 0.8 to the 15 minus 8. So this is 14, choose 7, times 0.2 to the 8, 0.8 to the 7. And this is 0.00184, etc. And so to 4 decimal places, 0.0018. And this is the answer for part C. So those are the problems that dealt with the fruit flies. So let's go to the, the next problem, which is problem number 5. And this is a longer reading problem. I took the information directly from the CDC's website, so be very careful. According to the CDC, it says more than 396 million doses of COVID-19 vaccines were administered in the U.S. from December 2020 to December 14, 2020 to October 4th, 2021. During this time, VAERS, which is a reporting system, received reports of 8,390 deaths. Now, this is 0.0021% among the people who received the COVID-19 vaccine. Now, these are all deaths. So the FDA requires the healthcare providers to report any death after a COVID-19 vaccination, even if it's unclear whether the vaccine was the cause or not. So reports of adverse events to VAERS following vaccination, including deaths, do not necessarily mean that a vaccine caused a health problem. That's very important. and a review of the available clinical information, including death certificates, autopsies, and medical records, has not established a causal link to the COVID-19 vaccines. They're not telling us whether there's an association either. But in any case, it's a very small number. And remember, these are deaths from all causes. So the number one cause is heart disease. So just realize that we can't make any real inferences about the COVID-19 vaccine and deaths caused by it from this information, and that was not my intention either. So we get to the problem now. Assume the number of doses of COVID-19 vaccine administered per week is a constant 3 million doses. So what I did was I found the data from a week, or so from a month, I think it was either a week or a month before October 4th. I couldn't find all the data very quickly, but I did find enough to say that the last week that there were about 3 million doses administered. So I know that the number of doses is not constant, and right after the vaccine was received the emergency approval, the vaccinations were very high. People were waiting to get their vaccination, and so that rate was much higher than it is now. So I'm massaging this data for this problem, so please understand that this is not a very scientific analysis. This is just to give us some experience using an approximate solution to the problem using the Poisson distribution, but not what we would normally do if we were analyzing this for real. Okay, we'd want a lot more information. So we're saying that we have a constant 3 million doses per week currently, and that the number of deaths in vaccinated persons follows an approximate Poisson process. So the mean number of deaths per day in vaccinated adults is approximately 9. Okay? So that means that, and if X equals the number of deaths in vaccinated adults per day, notice this is per day, and this is per week for the 3 million. So divide that by 7, and then multiply that by 0.0021%, which is 0.000021, and you get 9. This tells me that lambda is 9. That's the mean number of deaths per day. Oops, that's not very clean or legible. Deaths per day in vaccinated adults. And remember, for all causes, not for the vaccine necessarily. All right. So we want the PMF of X. So X is going to have a Poisson distribution with lambda equals 9. Now it's approximately Poisson process, and when it says that, we can take the mean number of occurrences in the same time interval, so this is day and day, then that is lambda. So lambda equals 9, so f of x is equal to lambda to the x, e to the negative lambda over x factorial. Lambda here is 9, so 9 to the x, e to the negative 9 over x factorial, where x can be 0, 1, 2, etc. And so this is the answer to A. It's our PMF with the support. So B is calculate the standard deviation of the number of deaths per day in vaccinated adults. Well, remember that sigma squared is equal to mu is equal to lambda for the Poisson, which is 9. So if sigma squared is equal to 9, then sigma is equal to the square root of sigma squared, which is the square root of 9, which is going to equal 3, another very nice number. Finally, C, find the probability that there are 10 to 15 deaths inclusive. So this is the probability that X is between 10 and 15. Okay? And so for this, we need a table. And I'm going to look real quick to make sure that I have a where I have a table available so that, oh yes, good. I do have the Poisson table here. Good. So I'm going to come out and go down to tables and go to the Poisson table. And remember that I have lambda is equal to 9. So we have this table from the book. The table has the CDF, not the PMF, but the CDF. So each of the probabilities in here are the probability that X is less than or equal to that number. Okay? And so we need lambda equals 9, and that's in the highlighted, or actually it was highlighted up here and it's not here. But here's 9, and we want between 10 and 15. So here is 15 and less, and here is 9 and less. So I'm going to subtract those two numbers. Why don't I subtract 10? Well, I want to include 10, so if I subtract off the probability that X is less than or equal to 10, I'm going to subtract off the 10. But I want 10, 11, 12, 13, and 14, and 15. So I'm going to subtract off that it's less than 10, and so I'm going to subtract off 9 and lower, and then I'll be left with 15 down to 10, or 10 up to 15. All right. So this is going to be, the probability that X is less than or equal to 15 minus the probability that X is less than 10. So what I'm doing here is I have 15, 14, 13, 12, 11, 10, 9, let's say. And so we have probabilities at each of these. So 15 less than or equal to 15 includes 15, 14, 13, 12, 11, 10, 9, etc. I want to be left with these 6 probabilities added together. So I certainly don't want to subtract off 10 and less, or I would get rid of this 10th probability, the value for 10, and I don't want that. So I'm going to subtract off from 9 and less, and when I subtract this off, I will be left with what I'm looking for, 10 through 15. All right, so I hope that's clear. And so in the table, less than 9 is, or less than 10 is equal to X less than or equal to 9. So I've got the probability that X is less than or equal to 15 minus the probability that X is less than or equal to 9. From the table, we saw that this is 0.978 minus 0.587, and the answer was 0.391. And so that is the answer for the fifth problem, if it was chosen. Now we're going to go down to the 6th problem, and unfortunately when I pasted it into my software here, it didn't paste very nicely, so I've rewritten the MGF, the moment generating function, for X, which is a discrete random variable. And A is find f of X, complete the table above for f of X. So I'm going to recreate the table here, and we have, so I've already said that it's 1, 2, 3, 4, 5, and then the total. So my table did not copy over very well at all. Now, I say hint, use the MGF to find each value of f of x and then solve for the constant c that makes f of x a PMF, a probability mass function. So remember, all the probabilities have to add up to 1. So when I look at the MGF, I see that this is 1t. So remember that it's e, the expected value of e to the tx. And so when I see the t left, the value that's multiplied by it has to be the value of x. And so for x equals 1, f of x has to equal 1 over c. All right? So I can use this MGF to find the value of f of x. So this is 1 over c. For 2, I have 4 over c. For 3, 7 over c. For 4, 10 over c. For 5, 13 over c. They all have a common denominator of c, and they all add up 2335. This has to equal to 1, and that's only true if c is equal to 35. So then f of x, I'm going to write it again, is, and this is what I was asking students to do, to give me each value of f of x, not to find the formula that goes with it, but just to give me the value for each, the PMF value for each value of x. So this is going to be 1 over 35, 4 over 35, 7 over 35, 10 over 35, and 13 over 35, which of course adds up to 35 over 35, which is 1. So this was the answer to A. B. Find e of x using the definition and the table above. Give the exact value, do not reduce fractions. Well, e of x is equal to the mean, which is also, from the definition, the sum of x times f of x. In this case, it's from x equals 1 to 5. So I'm going to use x times f of x like I did in the examples. And so I take 1 times 1 over 35, I get 1 over 35. 2 times 4 is 8 over 35. 3 times 7, 21 over 35. 4 times 10 is 40 over 35. And 5 times 15 is 65 over 35. When I add all of these up, I get 135 over 35. So this is equal to e of x, which is the answer to B. Now I say, use the MGF method to verify my answer from part B. Give the exact value, do not reduce the fraction. Okay. So the MGF method, I have m of t is equal to 1 over 35 e to the t plus 4 over 35 e to the 2t plus 7 over 35 e to the 3t plus 10 over 35 e to the 4t plus 13 over 35 e to the 5t, where t is in the real numbers. What we do is we take the derivative with respect to t of m of t, the MGF, and so we get the derivative of e of t is e of t, so I get 1 over 35 e to the t. The derivative of e to the 2t is equal to e to the 2t and then d dt of 2t, which is equal to 2 e to the 2t. I have to multiply that by 4 times, or over 35. So this is going to be 2 times 4 over 35 is going to be 8 over 35 e to the 2t plus 7 times 3 is 21 over 35 e to the 3t plus 40 over 35 e to the 4t plus 65 over 35 e to the 5t. And e of x is equal to m prime at 0. So when I plug in 0 into the exponent of e, this is 1 when t is equal to 0. E to the 0 power is going to be 1. So I end up with 1 over 35 plus 8 over 35 plus 21 over 35 plus 40 over 35 plus 65 over 35, which is, of course, 135 over 35. Okay. So that is part C. Part D, I want to find e of x squared. So I say use the MGF method. So I need m prime prime of t. So obviously I cannot take the derivative of these. They're all constants. So I have to come back to the first derivative and take the next derivative. I get 1 over 35 e to the t. 2 times 8 is 16 over 35 e to the 2t plus 3 times 21 is 63 over 35 e to the 3t plus 4 times 40 is 160 over 35 e to the 4t. 5 times 65 is 325 over 35 e to the 5t. We set t equal to 0. So m prime prime of t, we're left with the constants out front of each of the terms. So we 1 over 35 plus 16 over 35 plus 63 over 35 plus 160 over 35 plus 325 over 35, which gives us 565 over 35, and this is equal to e of x squared. And so that is the solution to the problem. Now, in the published solutions, I also went on to calculate the third moment, the fourth moment, and the index of skewness. Remember that the index of skewness used in our book, which is sk of x, is equal to the centered third moment, x minus mu cubed over sigma cubed, which is simplified e of x cubed minus 3 mu sigma squared minus mu cubed over sigma cubed. And I came up with negative 41,550 over 1550 square root of 1550, which is approximately negative 0.68088, etc., or negative 0.681. So it's slightly skewed to the left because it's a negative skew. Okay, so if you work that out, here's the answer in case you want to do that exercise. All right, so that's it for this in-class exercise, set number 3 on chapter number 2, which was the discrete distributions. Please take care of yourself and stay safe because we want to see you back here next time.